So we are going to see a little bit more details on the Wheatstone bridge, and we are going to see sensitivity of the Wheatstone bridge and how we can use it. Okay. Before start the class, I think that I have to start the recording as well. Now I remember before you, so yeah. Okay. So remember, when we start the description, of the Wheatstone bridge for strain gauge measurement, we found out that the relation between the output tension that we call E star and the change of the resistances, okay, was the one that I reported here at the bottom of this page, in which delta R1, 2, 3, and 4 are the variation of the resistances, because we are assuming that each leg of the Wheatstone bridge, that is each R resistance, are typically the strain gauge resistances. And so when we are having a strain gauge measurement of the strain using strain gauges, then we are having a change of the resistance. Because of this, we can have a change of the output tension from the balancing condition. Remember, we have the balancing condition that could be rewritten as balancing condition as R1, R3 should be equal to R2, R4. That is, whatever will be the input tension V, the output tension E star is always zero if the balancing condition is met. Then we also find out that in order to have a proper measurement of the strain, we must be smart in placing the strain gauges, okay? Because if you are using all the four legs of this Wheatstone bridge with four strain gauges, and then we place those strain gauges in a wrong way, then we can have always zero without any measurement at all. So just to remember that, I can write this very, very easy sketch. That is, you're having your whole structure like this, and then I place, for example, one strain gauge at the bottom and one strain gauge at the top of this reference structure. And then what we can say is that here we are having a negative change of variation at the bottom, the top, and a positive change of variation. So whatever is your number of active legs, you have to play with these. Of course, if you are using just one leg, the quarter bridge configuration, then no matter where you're placing this engage, because there is just one active leg. The other are not introducing any change of variation or resistance. Two, then you have two legs active, then you have to be smart, because you can have a compensation of the change of variation, so you can't measure anything. So you have to be smart, and this is the way you have to be smart. Three legs are not used. So four legs is the third option, in which we are having the right positioning of the strain gauges, so that you are not compensating the change of the resistance. If that is true, then what we can say is that when you are referring to this summation, you can rewrite that as equal to the summation through the active legs n of the relative change of resistance. Okay, like that. Okay, just a second. And if you are using the same strain gauge, sorry, the same resistances, you can write that as n times the change of resistance with respect to the actual value. Yeah, it will happen sometimes. User internet connection. If I can exit and re-enter, maybe. Okay. Can you hear me? Can you hear me?
Yes.
Okay. So, um, so you can rewrite that equation, that summation sign, as a number of the active legs. So the resulting output tension E star could be rewritten as the R over 1 plus R square. Remember, lower R is the ratio between R2 and R1. Times the number of active legs, and then your relative change of resistance, that is just given you by kg times epsilon. Okay, kg is the strain gauge factor, global or whatever, that refers to the Wheatstone bridge, that is being attached to the Wheatstone bridge. And the epsilon is the strain that has been the quantity that is the quantity that has to be measured, times, of course, the input tension. So as you can see, we have a very nice relation, linear relation between the unknown quantity, the strain, epsilon, and the quantity that could be measured, that is the output tension E star. Is linear and depends on the electrical parameters. R over 1 plus R is the electrical efficiency, as we can see later on, and the number of active legs, and of course the strain gauge that is being measured by its strain gauge factor kg. Now, sensitivity of this measuring circuit, remember, we are having that kind of measuring circuit, the Wheatstone bridge. The four resistances are placed close to the point in which we would like to have the strain, the measure of the strain. Okay, so we are referring all to the same point. It is a local measurement once again. The sensitivity S of this device, of this bridge, so that is sensitivity of the strain gauge measuring circuit that uses the Wheatstone is given you by the, as usual, the ratio between the output and the input. The output is your, let me write that as delta E star over the strain. Delta because it is referring to the output, to the balancing condition. Okay, so the difference between the reference tension and the output tension is equal to the output tension, because the reference tension, output tension is zero if the bridge is balanced. Okay, so it is equal to B over epsilon R1 plus R squared. Okay, and then N kg. Okay, and that is your reference definition for the bridge sensitivity with the constant tension, or the Wheatstone bridge with a constant tension. So here is the sensitivity is defined as the ratio between the output and the input. The output is your output tension, the input is the strain, that is equal, just going back here, to this relation, okay, to what's happened, what's remained out of this relation. Okay, as you can see, the sensitivity S depends on the number of active legs N, the strain gauge factor Kg, the feeding tension, constant feeding tension D, okay, and the ratio between the resistances, okay, R2 over 1. Okay, if we kept this constant, so if N, Kg, and V are constant, then the sensitivity is maximum if R is equal to 1. Indeed, if we are considering S sensitivity as a function of the ratio R over R, then you can easily see by yourself that the condition for which the derivative is 0, the derivative of the sensitivity with respect to the R is 0, that is local minima or maxima, is met when R is equal to 1. So for this condition, so when R is equal to 1, that is the optimal condition, maximum sensitivity condition for your strain gauge measurement circuit based on the Wheatstone bridge, we can say that if the number of legs is equal to 4, then the sensitivity is equal to kg times the tension, because R is equal to 1. Okay? And that is the full bridge configuration. If n is equal to 1, just one leg that is active, then the sensitivity is a fourth part of the maximum available. So it is equal to 1/4 kg times B. And that is referring to the quarter bridge configuration. Okay. Now, as you can see, by using this strain gauge measuring and the strain gauge measurement based on the Wheatstone bridge, we are able to measure the strain. Remember, the major issue was that the change of the resistance because of the strain was very, very small. Some hundreds of the ohms were required to be measured in order to have an estimate of the strain. By using this measuring circuit, the sensitivity is so that depends on the strain gauge factor, so it's order of magnitude of the unity is equal to 2, okay, times the input tension, that is some volts. So you are having, just by using some volts and the typical strain gauge factor, you are having a Wheatstone bridge that is giving you a sensitivity of some volts per microstrain, and therefore you are very happy about it, okay? Because it gives you the right sensitivity. You can measure this physical quantity, the strain, without noise, without any other issues. When compared, for example, with the typical tester non-bridge based measurement. So from this equation, you can also see that in order to increase the sensitivity, you can think to increase the input tension D so that you can have the required sensitivity for your typical measurement. Okay, but actually that is not possible. Why not? Because we are having an electrical circuit. We have to connect this strain gauge to the Wheatstone bridge. There is a current flowing to the strain gauge, and therefore we could have that all the measuring circuit is melt just because we are exceeding the maximum voltage that is the one corresponding to the maximum power that the measuring circuit could dissipate because of the heat, because of the Joule effect. So these values of the sensitivity are the good one without any information concerning the maximum dissipating power, okay? So it is the maximum that we have. However, in order to introduce the maximum power that could be dissipated, okay, from your measurement circuit, then we have to introduce this maximum power in your equation, okay? In order to do that, we have to distinguish between different operating conditions. That is one leg, two legs, four legs, that is quarter bridge, half bridge, and full bridge configuration. So let's see what happens when to the sensitivity when introducing the maximum dissipating power, okay? So Let's start with a quarter bridge configuration. Okay. We are having just one active leg that is the first leg, for which R1 is equal to Rg. That is, we are putting the strain gauge just on the first leg where the R1 is located. Okay, so going back to the general circuit here. Okay, so we are having R1, the only active leg, and the resistance is equal to the strain gauge resistance Rg.
So we still have the bridge itself.
We have the bridge, but just one strain gauge, that is the R1, in the R1 position. Okay, R2, 3, 4, or whatever, so that the balancing condition is met. Okay, you can play with R2, 3, and 4, but you have to be sure that R1 times R3 is equal to R2 times R4. Because we have to start with the balancing condition. However, it is your strain gauge measuring condition. Okay.
Value of that resistor is still measured in ohms, like I guess
Yeah.
heat creator again 5 times the strain gauge.
Yes, but you should measure the resistor, all right? But because you are using the strain gauge with the Wheatstone bridge, your output will be an output tension. Remember, here it is. That is the output tension and the strain gauge variation, the resistance of the strain gauge. Okay.
Okay.
So you are not measuring the change of resistance.
Okay.
You are measuring the change of the output tension because of the change of the resistance. Okay. And if you put the things together, you lead to this general equation, this one, and of course, the sensitivity is this one. Now, let's focus on that. Quarter bridge configuration, that is just one active leg. By definition, the only active leg is the leg corresponding to resistance number 1 in your Wheatstone bridge configuration. And for that, R1 is equal to Rg. Okay. If you remember, the input tension B is equal to the current flow in one part, I1, I call it. Okay, so is equal to Ig, that is the current that is flowing into the strain gauge, Ig, times R1 plus R2. Okay, just remember or go back to your notes at the very beginning of this. Okay, and that is the equation that we can say. We can rewrite that equation just by putting aside the strain gauge resistance. So we can say that this is equal to Ig Rg times 1 plus lower R. That is the ratio between the two resistances. Okay. Now, remember, because the dissipated power P through the strain gauge, so Pg, okay, is equal to the input tension times the current that is flowing through the strain gauge. Okay. And that is also equal to I square G times Rg. We can say that the current, the maximum electrical current that could flow through the strain gauge is related to the maximum power through this equation. Okay. Thus, what we can say is that the input tension is given you by 1 plus R. And then the product Ig times Rg, because of the power, could be rewritten as root square of Pg times Rg. Okay? Again, this is telling me that if your measuring device is characterized by a maximum power that could be dissipated, okay, equal to Pg, your input tension could not exceed this value. Okay, because otherwise your circuit could melt. There is too much heat over there, and therefore something will happen that is not good for your mission. That's about the sensitivity now. Let's go back to the previous equation and introduce this expression of the input tension. Is related to the maximum power. The equation is this one. Is it here? Okay. We have to rewrite this equation by considering now that n is equal to 1, number of legs. The input tension V is related to the maximum power, and see what happens. So,
Professor,
let me rewrite that as E is equal to R over 1 plus R square and kg. And then I should write V, okay, that is R plus 1 plus R square, that is equal to 1, so times 1, okay, then kg, and then V, that is the equation. So what we got here is 1 plus R times square Pg Rg. Mm-hmm. Oh.
Professor, I think, can you hear me now?
Let me see. Maybe. Can you hear me?
Yes, Professor, I can hear. Can you hear me?
Hello?
I'm speaking, Professor.
Can you hear me?
Yes, Professor.
Go ahead.
Okay, can you just draw a picture with one leg?
Stop. Okay, say, make your question.
Can you just draw a picture with one leg? I mean, the Bridgestone with one leg.
So your question is the use of different legs?
No. I mean, can you draw a picture?
Okay.
A picture with one leg.
and yes, Professor.
If you go back here to the basic circuit, okay. If you go back here to the basic circuit, you have 4 resistances to play with. Okay. You have to just substitute one resistance with the strain gauges. And these tiny strain gauges I showed you last class have to be put some places close to each other to the structure, okay? So that you measure the strain in one point of the structure, okay? So when you are using these strain gauges, you can have just 1, 2, or 4 strain gauges. We already discussed about that. That is, you are activating from the strain gauge measurement just 1, 2, or 4 legs. That is, in this summation sign, there will be just one strain variation in the resistance, delta R1, for example, and the others are all 0. Or we can have 2 variations, the half bridge configuration, that could be delta R1 and whatever other leg, and 4 resistance, 4 change of resistances that are all the 4 legs. Okay. I can barely hear you, so if you can write, if that is okay.
Can you hear me, Professor?
So at the very end, when I'm saying that I'm using just one leg, that means that I am just measuring one strain gauge. Okay, I have just one strain gauge, and that strain gauge is placed on the first leg, as I already told you. So the result in this case is that the sensitivity is given you by R over 1 plus R kg root square of PG RG. Okay, and that is the sensitivity that we can have when using your Wheatstone bridge with just one active leg, leg number 1, and by feeding this Wheatstone bridge with the maximum tension that is leading to the maximum dissipating power. Okay, so the maximum that we can have. We can't go further from the input tension point of view. Okay, now again, once again, if we are keeping the strain gauge and the maximum power the same, we have that also for this case, the sensitivity is a function of the ratio between the resistances, lower R. So the maximum.
Sorry, how do we, so little r, because little r is R2 over R1.
Yeah, lower R is R2 over R1. Is the ratio between the resistances. So the maximum sensitivity.
How does that equal 1?
Let's wait. Here we are just saying that there is one resistance with a strain gauge. So R1 is equal to RG. I'm just telling, I'm not telling other things. So R1, R2, R3, R4 should be, however, so that the balancing conditions are met. So R1 times R3 should be equal to R2 times R4.
Right.
That is RG times R3 equal to.
But R1 and R2 are different values.
Different values.
So how?
Different values, and indeed, these different values are taken into account by the lower R coefficient.
So I don't see how R.
Yeah, as you can see here, the output tension, the input tension is equal to Ig times R1 plus R2. Can you see that? Yeah. The input tension is equal to Ig times R1 plus R2. That is Rg plus 1 plus R times 1 plus R. Okay, here is R, lower R. And then just play with it. Okay. So if that is true, and it is, the maximum sensitivity could be obtained just by solving this equation. Finding the R so that the S over R is equal to 0. Okay, we can find that this is true when R over 1 plus R is going to have, is going to have a ratio equal to 1. Okay, so the maximum sensitivity for a Wheatstone bridge with just one active leg operating at the maximum dissipating power is obtaining when the ratio R over 1 plus R is equal to 1. This R over 1 plus R is also called the circuit efficiency. Okay, so we are having the maximum dissipating power when the circuit efficiency is equal to 100%, equal to 1. Okay, just to discuss a little bit of this, if R over 1 plus R is about 100%, that means that R is practically 1. Okay, and indeed, when we are having this value R, that means that R is going to have infinite values. Okay, so pay attention, because if you would like to have your Wheatstone bridge measuring circuit that is operating at the maximum sensitivity with just one leg and with the maximum dissipated power available, then you have also to take care about the fact that also R should be go to infinity value, and there should be some, let's say, issues related to the differential of potential between the resistances, because R is going to have infinite value. So R2 or R1 should be infinite. So one resistance is much larger than the other one. So care should be taken. Let's have an example, for example, just one example that we commented just after that. If R, for example, is equal to 9, so the ratio between the resistances is equal to 9, by the way, that means that R over 1 plus R is equal to 0.9, that is 90% of the efficiency. Okay, and the resistance is equal to 120 ohms. The maximum dissipated power is 0.15 watts. Okay, then what we can have is that the V is equal to 1 plus R to square of PGRG, that is equal to 42.4 volts. Okay, and the corresponding sensitivity is equal approximately to 7.06 volts over microstrain. Okay, so you can feel by yourself that the required input tension is very, very large. Okay, because 42 volts is not that, let's say, a small quantity. And the sensitivity also is very, very large, because we have just up to 7.6 volts per microstrain available for us. That is a lot of voltage. Okay. Some question? So when I'm referring to one active leg, once again, I'm not telling that there is just one resistance. All the 4 resistances are there here in the Wheatstone bridge. Okay, so there are still 4 resistances, are 1, 2, 3, 4. When I'm saying that there is just one active leg, I'm saying that there is just one strain gauge that is operating. So we have one strain gauge, RG, and R2, 3, and 4. Otherwise, there should be no Wheatstone bridge at all. Okay. I hope that is clearing you, Srivasan. Just give me a feedback in the chat room. Question?
Me? Yeah. Well, okay. Well, first, you want to do a break? I can ask the same question that I asked.
Okay.
For our break.
No, just question.
Okay. So we're saying little r, right, is equal to this R2 over R1.
Yeah.
And R2
could be whatever. Could be whatever. Right now.
Right?
Yeah.
So let's say R2.
You could have.
Right? And so that means our little r, right?
Yeah.
So in our equation, our sensitivity equation,
Yeah.
we plug in for D. 1 plus little r. I don't get how that equals 1. Like that, in that case, it would be
whatever. Could be whatever. The maximum, you can have the maximum sensitivity when that ratio is equal to 1. That is when little r is going to have infinite value.
Okay. Oh,
Okay.
okay. So we're looking for a max.
In this case, yes. If you have whatever value, the sensitivity is what you got.
Got it.
Okay.
Okay.
But the most important information here is that you're having the maximum sensitivity with the maximum dissipated power, okay, using just one strain gauge. And that is equal, according to our analysis here, so here we go. It is equal to this ratio. That depends on the electrical efficiency, R over 1 plus R, okay? And if you got that equal to 1, then of course you have the final result. Okay, let's have 10 minutes break and then we resume the class.